Good morning, good afternoon, and good evening, and welcome to the Friday Talk Show with your host Rajiv Kulkarni on Global Electronics platform. Yes, today's date is the 8th of May 2026, and we have crossed already 4 months of 2026, and we are in the fifth month of this year. The time flies, as everybody says, and I'm seeing that actually the time is flying. The global electronics main purpose is to bring wealth of knowledge that our veterans have gained over a period of their working years, their experienced years, I would say, and distribute it to the young generation or the engineers or the people who are designing, who are constructing, who are manufacturing, who are checking, who are testing, and who are working on the commercial side of electronics manufacturing market segment. And today's interesting topic is definitely, again, we have our the most appeared guest on our show so far, Mr. Ambaprasad from the Silicon Valley of India, which is called Bengaluru. That's the southern part of city, which is located in the southern part of state in India. And today's topic is physics-based interface routing. That is physics-based interface routing. And it seems to be a very, very interesting topic, as it usually refers to PCB or layout design for high-speed digital interfaces where you route traces based on electromagnetic physics instead of just geometric rules. And what is all this about physics-based interface routing and the application and so on and so forth? We have Mr. Ambaprasad, who has more than 40 years of experience in the electronics industry, in the design, in the various aspects of electronics manufacturing activities. Let's welcome Mr. Ambaprasad. Ambaprasad, good evening to you. How are you this evening? I think you are muted.
Yeah, now?
Yeah, now it is okay. How are you this evening?
I'm doing very good, extremely good. Let's go ahead. Not an issue.
Let's start our session for today. I will start presenting the presentation thing, and I'll share the screen right now so that you can then start discussing on each slide. Can you see the screen?
I can see the
Okay.
screen.
Okay, great.
You go to full size.
Yes,
and
yes.
go one slide behind. You are in sheet 109. Go to sheet 108. Go one back. Yeah. So this is where we stopped our
Last
previous
conversation.
talk.
Yeah.
So in this previous talk, we told key similarities across guidelines, recommendation, and standards. Standards means including multi-supplier agreements. So we listed the risks and how recommendations are, when to use recommendations, when to use guidelines, when to use standards. So now let's start unraveling them. And I am just taking sort of what is similar and what is not similar between guidelines and recommendations, and standards we may cover a little later. So with that, I started guidelines. Guidelines were there since last 40 years or 50 years. As long as PCBs were routed, guidelines were there. People depended on them. Let's go. Let's discuss. Next page, please.
You want me to
move the slide. Yeah. So sort of in the next page, we have a pictorial. It says why we have to do a physics-based calculations, especially people were doing it in their pre-layout simulation. But that, as you said earlier, this was basically geometric, but now it is physics-based. So the agenda for reliable high-speed interface boards, the best approach is to execute physics-based interface routing. Must be using advanced ECAD for simulation as well as layout. Just taken PCIe SIG as an example, uh, because it is a 30-year-old protocol. They celebrated 30 year this year, which is good. Then physics-based differential routing, I'm covering. We are also covering why attenuation is important, especially in traces which are quite longer, especially in a backplane. And then when we are doing these two things, we are taking some material properties into consideration. In spite of doing material properties, plugging in the data, doing simulation and routing properly, there is what is called as a material crisis induced due to AI cycle. So how AI and hyperscalers are controlling the market, that sort of a, I'm just giving a, it's not hypothetical, but it is really, it is happening. So let's go to next page, please. So now I told earlier also, we never talk about a length of a trace. We talk about the timing. And again, we talk about when we cannot meet the timing or if you have any signal integrity issues, it translates into losses. So we are telling so many, there's a loss budget whenever you do a constraint management. This are taken from PCIe 6, which they're getting into PCIe 7 also. It is in the pipeline. So the total channel loss from, I look at the left bottom, we see the driver. Then we are having the trace running through a PCB. Then there is a retimer or something. Then it is going to the module, the package. So whatever it is. The total loss is 32 dB. If we cannot meet this loss budget, and this loss budget 32 dB is considering all manufacturing variations, assembly variations, material, sometimes they misbehave, keeping everything into consideration, 32 dB. So in 32 dB, at least another some 10%, that they are given a breakout. So PCIe 6, PCIe 4, it was 20 dB at the package level. And PCIe 5, it became 26.5 dB. PCIe Gen 6, it is becoming 23.5 dB. And then again, package loss, it was a 5 dB in 4, in Gen 5, 8.5 dB, in Gen 6, 7.5 dB. So as the chips became faster and faster, they're using more energy to operate and to drive the traces, the signals to drive across the traces. So even your losses are increasing. So what was a 5 dB loss? Now it is almost another 50% more. The channel loss, again, we are seeing almost, channel loss is remaining the same because there was a lot of improvement in PCB material. So channel loss is 15 dB, Gen 4, Gen 5 is 18 dB, Gen 6 is 15.7 dB. This number can be sort of confusing because sometimes in a PCIe, they want to have a reverse compatibility, backward compatibility. That's why they might have maintained, because they want to insert the same package in a next year. For example, PCIe 6 package, they want to put in a board which has been designed for PCIe 5. That's why they are consistently maintained the losses also. There is no change, not much change. Then we go to the package at the receiver. Package loss was again 3 dB, 4.2 dB, and 4.1, almost a 25% increase over there. Channel loss 5 dB, 5.3, 4.4, not much change. So they're controlling by the same PCB can be used for Gen 6 as well as Gen 5. The same routing can be used. And then the total loss that across the channel, they're taking which was 8 dB at PCIe 4, but they went up to 8.5. But this cannot be guaranteed in PCIe 7, because if you look at the difference, PCIe 7 is talking of 128 GT of transfer. It's a huge leap, actually. So it may or may not be backward compatible, 7 to 6, or at least 8 is in the pipeline. 8 also may not be backward. That is the apprehension, but we cannot know, because PCIe being a 30-year-old organization, they may come with a magic at the last moment and they may say, do this, it works. That's it. So I'm talking about losses.
Okay.
So let's go next slide, please. So here, even something like 3.125 gigahertz onwards, geometric calculations will not work. What works is physics-based design rules. So we are talking of a physics-based differential pair routing. Differential pair routing best practices. This is not a guideline. This is not a recommendation. This is not a standard. This is a combination of all the three. I have taken best of all every three and put it here. Rules, basically the main idea is to common mode noise has to be solved and avoid EMI. Then phase matching intra-pair skew in multi-gigabyte lines, plus or minus 1 mil we are talking about. Then the 3W rule. And going forward in a few episodes, we are making fun of 3W rule. It works under certain conditions. In certain conditions, it won't work. So that I'm going to unravel that. It says greater than 3W now. Not exactly 3W, greater than 3W rule to avoid crosstalk. Then impedance control, 10% no longer works. It has to be 5% or 8%. And symmetry. Symmetry, this is where geometry plays a key role. There should be a geometrical symmetry between P line and N line. So this is very mandatory. It has to be almost like a mirror image. So this is about, go to next page. So whatever I've shown in the picture, just put in text over here. Maybe we'll give a minute of time for people to digest this.
Yeah.
Makes sense. Differential pair routing, engineering best practices. We have told the main idea. Whatever I have told, I have put in text over here. If there is any difference due to geometrical mismatch, it will give a common mode. Then impedance control, 85 or 90 ohms. Symmetry is mandatory. Gap rule, greater than 3W gap between a differential pair and a single-ended line, and even between two differential pairs. Phase matching, when we say, some people follow, when we say 1 mil, it is 0.0254 mm. Some people follow 0 to 0.0254 mm, but some people follow minus 0.125 to plus 0.125. So that's how people differ in different ways. And then use phase bumps, small meanders near the source. And actually this, there is one theory that this phase bumps, if you don't put within 20% of the electrical length, it no longer works. The bump will be there, but it doesn't work. It is to be most effective. The bump has to be put within 20% of the electrical length of the trace. Yeah, that's it. Next slide, please.
Wow, this is a fantastic picture.
This is a very good slide.
Yeah.
So here we are talking about skin effect, dielectric loss, because since we are using advanced material, on the left side they are given the causes, on the right side they are given a mitigation. Copper roughness plays an important role. Copper has to be very smooth, and they have shown HVLP we have to use, ultra low loss material they are given, and again we use normal material, it won't work. So they are given just an example. That's how it works. Skin effect, conductor loss, and dielectric loss. Dielectric loss happens at the surface. The dielectric will absorb some of the energy. Conductor loss is if there is any roughness or something, it is a resistive loss. This is a very good picture generated using AI. It's a nice picture.
Beautiful. So I just want to request the audience, if you are watching this show, please do put any questions that you have in the comment section of our YouTube channel that you are watching. So that way, we are able to answer your questions if possible in this session, or we can come back to you. Okay, now I'm going to the next slide.
Okay, adding to your request, they can say the slide name actually. Is it attenuation or
Yeah,
physics based? Then it will
yeah,
be very
slide
easy.
name, or they can put in general also any questions if they have.
Yeah.
Subjecting,
Then the same thing I explained here, signal attenuation at high speed I/O, especially on a backplane. At frequencies about 10 gigahertz, tracers act more like a leaky pipes than wires. Attenuation is the sum of two primary laws, skin effect as well as the dielectric loss. Copper loss is at skin effect. At frequency increases, current stays at the edge of the copper at the surface. Mitigation use very high profile, very low profile copper file, not high profile. The high profile is high pricing actually, but low profile, the thickness is almost, they are telling it is almost no thickness. That is the technology name they follow. Standard rough copper creates a longer path for the signal. It is like, you are driving your vehicle. Imagine you are driving your SUV on a airport where planes take off. Jeep can go faster because road is well maintained. But if you ride it in a normal road, all those bumps and rough surface, that creates a problem. It is something similar to that. Dielectric loss, tan delta. This is very, very much important. Dielectric loss is much more important than dielectric properties. The PCB substrate, normal FR4 absorbs energy due to molecular friction, but in smooth, the material with less dielectric loss, the materials will align properly. Mitigation, transition from FR4 DF approximately 0.02, it's a number, to ultra low loss material like a Beg9 or a Tachyon, two popular brand names. 00N, 3 decimals is the dielectric loss at 100 G. Because in the data sheets, the simulation is done at very low speeds. Very few vendors, especially these two vendors whom I am mentioning here, they do at 1 gigahertz, 5 gigahertz, 10 gigahertz, 100 gigahertz. They give you the number. If one looks at the data sheet, they can know the difference, is what it is. I think maybe after this we can take a break.
Okay, I will then run a quick video and then we'll come back. Good morning, good afternoon, and good evening, and welcome to the Friday Talk Show with the Global Electronics and your host Rajiv Kulkarni. Today's date is May 8th, 2026, and today we are talking about physics-based interface routing, which is being presented by our veteran electronics design professional technology expert, Mr. Ambaprasad, who is based out in Silicon Valley of India, which is called as Bengaluru City in Karnataka state. So Global Electronics brings in every week some different topic on electronics manufacturing, whether it can be design, the development, the R&D, the test methodology, or the manufacturing activities, supply chain, and the commercial aspects of it. So it's a commercial free channel, and we are here to support the electronics community. So Mr. Ambaprasad, welcome back after this small break, and let's continue our discussion, and I will share the screen right now. Are you able to see?
Yep.
Okay. So
Go to the next slide, please.
next
Go to
slide.
full close.
Yeah. Oh, again, it's a beautiful slide.
Yeah. So again, we have got only 2 slides to talk now. We have 10 minutes of time.
Sure, sure, sure.
But here, it takes 10 minutes for someone to understand the concept what I am telling. Maybe 5 minutes to explain the second sheet and first some 3 minutes to understand. Again, I'm giving time for people to look at the slide and try to figure out what's happening in the industry. Number one. And Raju, believe me, I did a lot of English to English translation to make this slide look as humble as possible. The first set of slide gave a very, like a critic, it was uh, throwing away some sort of a Clint Eastwood language. It was trying. I redefined, and I don't want to hurt anybody, or I don't want to scare anybody. But this is what it is. So crisis due to AI cycle. So almost now 30% of the uh, make ultra high-tech design is happening on AI backend only. All these big 5 companies are controlling. That can be another discussion. That's not an issue. But again, since last 1 month, 3 new multi-service agreements have come to just to cater to AI data center hyperscalers market. So it is very aggressive actually. And again, what's happening at one end, 2026, AI, high density interface, ultra high density PCBs, and material crisis. The material shortage here, let's start with the material shortage. All high speed material has been booked by AI companies, or the people who are doing layout for them, PCBs for them. So low decay glass used in AI servers. So the lead time, what was something less, maybe half of this has become 18 to 22 weeks. Number one. Number two, why this? Because even the chips, what they are doing, they have to test it. To do the testing, they have to do a test board. The test board also can be something like a 60-layer board. So that's what it is happening. And again, copper and gold price. Gold always surges, that everybody knows. Copper surging again. Data centers are consuming a lot of copper for power distribution, bus bars and cabling and power cabling and whatnot. So there was a heavy copper. In fact, copper was accelerating more than gold in terms of pricing. In fact, in the futures, people were hedging on copper. So there was a good spike on copper about 3 months back. So this started almost a 30% price increase in copper itself. Forget about gold. Then again, a lot of specialty chemicals, a lot of petrochemical derivatives are used in high-speed material. And due to geopolitical, whatever global tensions, they can be, though the material is available, one has to ship a material from point A to point B. This can be a raw material, this can be a finished material, this can be anything. So everything is, there is a perfect storm to mitigate, to in fact, to make this crisis more deepen actually. That's happening. The AI impact, all motherboards are moving towards 40 to 60 layers, even test boards and motherboards. Consumer consumes global ultra-thin prepreg material supply. All supply is booked, impacting standard PCB buyers. So all big companies have booked the material. High density interconnect and ultra high density interconnect. This we covered a lot in last year, but whatever we prophesized last year, prophecy came true this year at least. Lead space, the trace spacing is less than 1 mil. Trace width is less than 1 mil. Becoming standard for 1,000 plus pin AI accelerators in the redistribution layer. Requires modified semi-additive process. Centralizing supply chain, and even not only supply chain, even your the CAM machines, people who are doing a CAD and CAM layout, verification, DFM, everything is blocked. And most of the work is happening in Southeast Asia. In fact, we are seeing a lot of traction in Southeast Asia. Maybe after another 3 months, we are conducting a lot of training and sort of things over there. It's highly booked. We are seeing a lot of traction from Southeast Asia. Globally, it is growing, but Southeast Asia is growing by leaps and bounds. Let's go to the next page, please.
Crisis
So
due
this is
to
the last
AI
page.
cycle.
Yeah, that's whatever I have shown in the picture explained. Material crisis, AI super cycle has fundamentally broken the traditional PCB supply chain. Material shortage year 2026 has been projected, and it is coming true. Copper and gold prices, not only price, even supply is an issue. AI impact, AI motherboards, especially used in the back end, are moving towards 40 to 60. Actually, in AI, what happened is there was a scale up and scale out and scale across. They require a lot of cabling, a lot of optical cabling, a lot of power supply. So that is where the copper is used. Optical cable they are not using, but still on the power supply side, still they depend on copper. Then ultra thin prepreg, everything has been fixed. Again, PCB buyers facing price hikes even for simple boards. To accommodate 1,000 plus pins in a AI accelerator package, ultra HDI line spacing, line width and spacing less than 1 mil is becoming a standard. This requires MSAP process, and with a few Western shops can get this. And that's why everything is pushing to Southeast Asia. Not only there is a huge pressure on CAD, there is a huge pressure on CAM, and also on manufacturing. So these are the things. Nice time to be in the industry, exciting time, but it remains. So what worked
Yep,
3 years will not work anymore. So this is the first
absolutely.
part, but I'm going to unravel everything one by one in the subsequent stuff. I kept slides, only 8 slides, because I wanted to do more explanation. I wanted the people to look at the picture and understand what we are trying to project. So this is going to be the way forward. We are going to show pictures. If I show 8 pages, 3 pages will be pictures now. So that I think that's way this brings a lot of ideas. So that's it. Any questions, any comments we can answer now, or we can answer a little later also. No problem.
Absolutely. So with that, I'm going to stop sharing the screen and let me see if there are any questions. That way we can take care of that. For CPWG differential routing, is there any benefit of using wider traces, that is approximately 0.3 millimeter, with wide gaps as compared to narrow traces approximately 0.16 millimeter with narrow gaps? I have to place inline DC blocking caps also. This is the question.
So this question I faced myself 10 years back. I got the answer. So there is when we do differential, thanks for the question. I mean,
Yeah,
I like it very,
it's
I
a
like
great
it.
question.
It's an excellent question. When we do differential, actually that's where I put in 2-part answer. First, I will tell you the guideline will say something, the application note will say something else, and standard will say something else. So the doubt has occurred. And if you take a skin effect, my slide when I told attenuation skin effect, obviously one has to use a wider trace, need not be a thicker copper. People can still use half ounce of copper in the PCB, but the trace has to be wide. Even if your simulator throws a 5 mil trace, something like a 5 mil trace, a 6 mil gap, better you go for a 6 mil trace, because a 6 mil trace gives a more skin than a 5 mil space. Number one. Number two, one has to educate the PCB CAM vendor. My way of getting a wider trace was I always spec for a 95 ohms in place of 100 ohms. Naturally, it becomes a wider trace. Now, many PCB CAM vendors told me when I was handling things, I'm giving you perfectly 100 ohms. Why you want to asking for 96 or 95 ohms? I told, "Boss, this is my way of getting a wider trace. This is another way of getting a wider trace, plan B. But again, there is always what is called as tightly coupled differential pair and a loosely coupled differential pair. This can be another topic another day. That's okay. But looks like the person who asked the question is using a loosely coupled differential trace. And maybe I think he's doing a very high-end board. Looks like the way the question has been faced. Anyway, they can call me also directly, not an issue, over my phone. Or they can
Great.
put a question to the channel. We will definitely answer this. This is a very good question. Go for a wider trace. Go for a very smooth copper. Even PCB vendor or a CAM vendor will give you something like a 100 ohm, pure 100 ohm. You tune it to 96 ohms. We are getting a bonus extra few microns wide. That will definitely help you on the day. So that's it. Yeah. That's
Okay.
good. Good question. I like
Great,
that.
Ms.
I
Ambaprasad,
hope
and
I
thank
answered
you.
the question. Person is
Yeah.
convinced, he can put a
Yes.
you can put a thumbs up mark or something.
Thumbs up. Yes.
Oh, that's
So
good.
I hope the question was answered to your satisfaction. If yes, just put a thumbs up so that our guest feels good as well. Okay, so I think they will do that probably at the later stage. With that said, I think we are coming to the end of today's session. And next week thank you for the answer. Had a call. Okay, he had a call with you sometime back already, he says. Anyway, that's
I
good.
know who is this. I
Okay,
know who
okay,
asked the
great.
question.
Okay, great, great. Thank you very
No,
much.
but
And thank you all the audience for watching the show today. And keep tuning Global Electronics for more interesting topics. And next week we will be having something to do with the manufacturing. So please come back. And also, I would kindly request, please subscribe the channel so that you can scroll down and look back on our various topics that we had in the past. And Ambaprasad has been our great guest and always been a supportive individual, professional, and serving the electronics industry for more than 4 decades. And with that, I want to sign off for today's session. And wherever you are, please take care of your health. And we will see you next week at the same time. And with your host, Rajiv Kulkarni and Global Electronics. Thank you very much. Thank you, Mr. Ambaprasad.
yeah, thanks. Yeah, that the difference between loosely coupled and tightly coupled can be another topic some other day.
Another topic. Yes.
That really helps. Yeah.
No,
Good.
I
Thanks
think
for the question.
we can definitely segment it in 2 or 3 different sessions, picking one topic at a time. So that would be great. Thank you all. Have a great weekend.